Hello and welcome back to another episode of Math with Son. Today we're going to be doing a circuit problem. This one is from May-June 2024 and it is paper 2-1 in physics. So, what is Kirchhoff's first law? Remember that it is alphabetical. The first law relates to current and the second law relates to voltage. Okay, so the first law with current is whatever goes in must go out. So the sum of all current going in to a junction must equal the sum of the current leaving that same junction. Okay? And that is the first law. The second law is going to be covered in the next problem. It says a cell with internal resistance R, that's this guy. Normally the internal resistance is a lowercase r, and then the external resistance is normally dedicated with bigger r's. In this case, we have two external resistors. Okay? And is shown in figure 6.1. The potential difference is across R1 and R2 are V1 and V2 respectively. So I am going to write that now. So the voltage, if we put up a voltmeter here, would be V1. And if we put up a voltmeter on either side here, it would be V2, representing the voltage drop for that. Okay? The terminal difference across the cell is V. So if the terminal difference across the cell, that means if we hooked up a voltmeter on either side of here, from this side to this side, it would read V, which is not the entire electromotive force. That would be the voltage at the terminals. The electromotive force would be like if you went from here to here on either side of the battery, that would be the entire EMF. Okay? So we're excluding the internal resistance, so this voltage at the terminal is going to be slightly less. All right. Using Kirchhoff's law, show that the total resistance, RT, of the external circuit is given by RT is equal to R1 plus R2. Okay, so I'm going to start with Kirchhoff's second law. Remember, the second law is voltage. Okay, so the second law is voltage, and the voltage that completes one loop, which would be from here all the way across, which is also represented as the shorter path from here to here, would have to equal these two voltages added together. So that means that V would have to equal V1 plus V2. All right, that's essentially the easy part of Kirchhoff's second law. And then you can rewrite that as V, the total voltage, is equal to I, just regular I, times R1 plus I times R2. Okay, and that is what I would normally stop with, but that's not really what is here. So this says resistance total is equal to R1 plus R2. By the way, the reason I can rewrite this as I times R is not due to Kirchhoff, it is due to Ohm's law. Ohm's law is I is equal to voltage divided by resistance. That is Ohm's law. And if you multiply I times R, you get voltage. So we just replaced voltage with I times R. So we could also replace voltage with I times R here. And this would just be I times R total, or RT, I smudged, would equal I times R1 plus I times R2. And then the fancy thing here is like, well, wait a minute, everything has an I, so they could all cancel out, and you get R total is equal to R1 plus R2, which is essentially what you do when you have resistors in series is you add their resistances. You would add the two resistances to get the resistance total. This was a very fancy problem, but I did like how it kind of just tied everything together. And that is all it is. It's only a two-pointer, so we're going to move on. The electromotive force of the cell in figure 6.1 was 1.5 volts. Okay, so it was 1.5 volts. The values of R2 and R1 are 10 and 15. The terminal potential difference is 1.35. Calculate the internal resistance of the cell. So I'm going to have to like fill in the things, and then I'm going to go back to the diagram and then go from there. So we have it said that the entire EMF, so the voltage here was 1.5 volts. I'm just going with what I just read. it said that the voltage at the terminals, so this voltage was 1.35. I mean, I'm going to have to double check that, 1.35. And then we have 10 ohms and 15 ohms for the two resistors. So this is a 10 ohm resistor and this is a 15 ohm resistor. And we want to figure out the little r right here. And you got a bunch of options. I think the easiest thing to do is maybe figure out what is the current, okay? So we're going to start out with just this portion right here because we don't know the current, but we do know the voltage at the terminal was 1.35. And we know the resistance, R1 and R2, were 10 and 15. So the voltage at the terminal, 1.35, would equal 10 times I1, or I, plus 15 times I. Now, you don't have to do that. You could have just used Ohm's law and thought, okay, well, the voltage total, 1.35, not the EMF, but the voltage total, 1.35, and the R total would be 10 plus 15, which is what we're going to do here. We'd have 1.35 would equal 10 plus 15 is 25I. And then you divide 1.35 divided by 25 would equal the current. And that is an important value, which is all it would be is Ohm's law, voltage total divided by resistance total equal I total. And the voltage at the terminals was 1.35, and the resistance outside the terminals was 25. So it's the same thing, 1.35 divided by 25. 1.35 divided by 25. I need a calculator, or I could cheat if I have it on my thing. I don't. I have to do it in my calculator. Answer key didn't show you. 1.35 divided by 25 gives us a current of 0.054 is the current amps. Would equal the current. Now that's an important value because if we know that, we can figure out the internal resistance because we also would know that the current going through it is 0.054 amps. How much voltage is this little r taking up? Well, if the voltage on the outside is 1.35 and the voltage total for the EMF of the battery is 1.5, that means we could subtract them because this has got to use up whatever the other two didn't. So if I do 1.5 minus the 1.35, we get that the voltage of the little tiny internal resistor is going to be 1.15 volts. So let's do the math there. The voltage of little r, the voltage was 0.15, and the current was 0.054. Well, I can use I is equal to V over R to find the resistance. So I is 0.054 would equal 0.15 divided by little r, and we could solve 0.15 divided by 0.054 ends up equaling a little resistance of 2.77 ohms, or 7 repeat, really. And we would round to 2 sig figs there, which would give us an R value of 2.8 ohms. And we do think that we would have had to do some work. That was a 3-point question, so that took a bit. All right. Let's do the next part. We're almost done. 8 minutes. That's not bad so far. A resistor of resistance R3 is added to the circuit. So we have R3. Notice how it is hooked up in parallel. Anytime you add a resistor in parallel, or resistors in parallel, the overall resistance total goes down. Okay? That is different than if you changed the R3. So currently, like we added this one in parallel, the RT, the resistance total, is going to go down. If I decided later on to change R3 to a bigger resistance, that would actually create a more resistive value. So the only time the resistance total will go down is if you continually add more and more resistors. So if I added another resistor in parallel, if I added a third one over here that was added a third parallel section, that would also bring the resistance total down. But if I just change any of these resistors to a higher resistance value, that would cause the resistance to go up. Okay? It's only when you add more resistors, not when you add more resistance to those resistors. If you add more resistance to those resistors, resistance total goes up. If you add more resistors, resistance goes down. I hope I made that clear. I said it like 10 times. All right. State and explain the effect, if any, it changes to the current in the cell. Well, we just said that the resistance total will go down. Anytime you add resistors, not resistance, in parallel, resistance total will go down. And resistance total would be inversely proportional to current. So we have voltage, which is not going to change, divided by resistance. If we know that current is inversely proportional to resistance, then the current will increase. Okay, you could also think of it logically. If you decrease the current, if you decrease the resistance, it's going to make it easier for the battery to have more current. Okay, so resistance total went down, therefore the current, the current will increase. Okay. What about the terminal potential difference? Well, think here. We could also think in terms of the formula. I is equal to V over R. The current went up, but the voltage is actually going to be going, if we solve for R, we got I times R would equal voltage. R is directly proportional to voltage. So if R goes down, voltage would have to go down as well. That's like using the formula. But if you don't want to think of the formula, when you take this section on the outside and you make the section on the outside, all of this stuff on the outside, have less resistance, it is going to draw less voltage. In series, whatever has less resistance gets less voltage, which means that the little r will essentially gain proportionally more resistance and will draw more voltage of the battery. Okay, so originally the voltage on the outside was 1.35. Now it's going to be something like 1.2 because the little r on the inside now proportionally has more resistance before. So the potential difference will go down. The reason it will go down is because the resistance on the outside between R1, R2, and R3, that resistance total will decrease. And those are directly proportional to V. I am curious to see what the answer key says. It says, as the current is greater, larger potential difference across the internal resistance, and the potential difference across the outside will decrease. So I said it, but I said it in a lot of words. I didn't write the answer necessarily down. I wanted to go through all the things. Until next time, stay positive, my friends, and I will see y'all later. Bye.